So top of page 2 here. Here officially in your notes we have the idea that ln refers to the natural logarithm and is representing a log base e. So we have the natural logarithm with e being the natural base. ln may seem strange, like why didn't they call it NL for natural logarithm? Essentially, when this was first discovered and used, it was in a language where the appropriate phrasing for this was logarithmic naturalis, so ln. So that's why we're using it backwards in a sense, or it feels like it's backwards. But as far as what we're going to do in these next problems, it says determine the value of the logarithm without using a calculator. So notice now we've got some logarithms and we don't have them written as an equation already. So we aren't just converting it, but we're going to use that trick to say, here's something we want to know the value of. Right now we don't. So we're going to make it into an equation and say, pick a variable, I'll pick x, as the value we're trying to find. Determine what this value is. But as soon as you turn it into an equation, then you can do the cycle. You can use the cycle to convert it. 3 to the x equals 81. That would be the exponential form of that statement. Now, why is that better? X is trapped in an exponent here, right? We have no ways to solve for that right now. But what we do know is we're looking for the exponent of 3 that would give us 81. If you can look at 81 and ask, is that a power of 3? It turns out it is. 81 is 3 to the 4th power. And if we can get to there, if we can get to 3 to the x equals 3 to the 4th, then that means we see right there x must be 4. Right? If 3 is raised to the x, and that gives us 3 when it's raised to the 4, then the only option is that x equals 4. And now just to kind of point this out here, we put in x, right? X was never a number, a variable. It was not an equation we were solving. We used it to figure out the number. So really, determining the value, I'm just going to put the number 4, as in that is the value that log base 3 of 81 is equal to. If anything, you could write this is log base 3 of 81, right? That's what we just did. We found that value. But that's the trick we're going to use, the process we'll use for all of these. So the next one. Think of it as an equation equal to x. Use the cycle. 5 to the x equals 1/25. Okay, so in this case, we could look at 25 and say, wait, 25 is the power of 5. Let's do that first. 5 to the x equals 1 over 5 squared. 25 is 5 squared. Now, the problem is these aren't quite comparable yet because this is stuck in the denominator right now. So we can use a trick about exponents to move it to where it doesn't technically belong. And 1 over 5 squared would be the same as 5 to the negative 2. Right? That's our trick of changing the sign of the exponent if you move the base to the other side of that fraction bar. But now we've got 5 to the variable equals 5 to the negative 2, which would mean the variable has to be negative 2, which means this logarithm, log base 5 of 1/25, is the value negative 2. Let's look at these next two here. So when I see ln of e, I'm going to go ahead and immediately rewrite that as log base e. We're going to want to see that base to use this cycle. Now, log base e of e equal to 1, equal to x. And now the cycle, e to the x equals e, is our exponential form. And that's already the same base. And you can just think of anything as that base to the first power, e to the first power. And so that tells us that x would equal 1. So ln of e is equal to 1. And this is another property we'll actually look at here in just one moment. And then the last one here, log base 9 of 3. So again, what's it equal to? Then use the cycle. 9 to the x equals 3. Now notice, this is not saying 3 to the x equals 9. This is not saying that you could square 3 and get 9. X is the exponent of the 9. Question of what would you do to a 9 to make it a 3? here's where you got to think back to what we mentioned on the first section. Don't forget a type of exponent we have. We have fractional exponents that represent radicals, right? Square roots, cube roots, etc. So this 9 to the x, if I'm trying to write this 3 as 9 to the power, I could think of this as 9 to the 1/2. I could think of 3 as 9 to the 1/2. Now that'd be one way to do it. And there you see x equals 1/2. All right. Another way to do it is if you've got this 9 to the x equals 3, is think of 9 written with the base of 3. What is 9? 9 is 3 squared, right? But then 3 to the second to the x, there could be our power rule there to get 3 to the 2x equals 3. So we could rewrite this 9 as the same base, and now you could compare 2x to 1, saying that 2x is the same as 1, 2x equals 1, divide both sides by 2, and get the 1/2 that way. That's more work, but maybe instead of trying to see the square root that isn't there, it may be easier to see the power that is, and then solve for x to determine what the value will be. Because again, the answer is just the 1/2. Log base 9 of 3 is whatever x is, which was 1/2. So you can either go this route, trying to turn this back into that base using a fractional exponent, or you can go this route and solve for x where you get the fraction. Either way. All right, the next 4 things are 4 properties that we want to be aware of. The first 2 here just kind of follow directly along with the understanding of what the logarithm is saying. Logarithm base b of b. When your base and your what we call argument of the log, or input, when they match, log base b of b, that will always be 1. And it says because 1 is the exponent to which b must be raised to obtain b. In other words, if you use a cycle, b to the first equals b. Just like we saw up here, e to the first equaled e, right? That was that example right there. That works for any base. When the base and the argument are the same, you get a 1. Also, if you have log base b of 1, that's always going to be 0. So any base of a logarithm, if it's of 1, that's going to give you 0. And again, for the same reason, think the cycle, anything to the 0 equals 1. So those 2, again, just come from understanding the cycle and understanding that no matter what b is, those 2 things will always be the case. B to the 1 is b, b to the 0 is 1. That's always going to work. The next 2 are the inverse relationship between logarithms and exponents, and they look kind of confusing, but we can use them to our advantage at times. Generally speaking, I don't end up using these properties very often, and I really just rely on the cycle trick. But we do want to know that if you take log base b of b to the x, so this was log base b of b and it was 1, but log base b of b to the x, as long as that base and that base match, you actually get out the exponent on that term. So you're left with just that x. And then here, if you have log base b of something, but that whole thing is the power on that same base of b, so b to the log base b of x, if those bases match, that's another way to get just the x out of that. And so these are tricks, these are properties we can use whenever we get some more complex things look in our problems, especially in equations. We can use these to really simplify things, and you'll see that later on in the chapter. So using those 4 properties, when I see log base 7 of 7, you can certainly do the cycle we were doing up above, or if you've memorized and understood this property, we know that log base anything of that same number is just immediately equal to 1. There wouldn't need to be work there because we know that. Okay? Same with this one. Log base 5 of 1. Well, we said log base anything of 1 is immediately 0 because anything to the 0 is what it takes to get a 1. So those are both, again, ones you can just know the property of. And then same with this. If you recognize this as the log base 4 of 4 to the power, when this base and this base match, that rule right up there is telling us when those match, you're left with just that exponent of 5. Oh, I'm sorry, off the page. Log base 4 of 4 to the 5th. When those bases match, you're left with the exponent. And then this, probably the most convoluted one, where you've got a base raised to a logarithm. If that base and that base match, you're left with the number inside of the logarithm. So those 4 examples are really just using each of those 4 properties.